Hi, Lasky here. Welcome to my channel, MalfindLabs. After a long break, I decided to resurrect my channel to talk about the research that ESET published in August this year. ESET discovered the first known AI-powered ransomware, which they named PromptLock. The PromptLock malware uses the GPT-OSS-20B model from OpenAI locally via the All-Llama API to generate malicious Lua scripts on the fly, which it then executes. This malware was later discovered to be just a proof of concept. Still, the discovery generated a lot of media buzz and debate about its real-world applications. But I've never seen anyone actually testing the malware itself. It's time to find out if this AI malware is a real threat or just a gimmick. We're going to see if it can actually complete its mission and how well it performs. Spoiler alert, I expected it to struggle, but I had no idea it would fail this spectacularly. What we will need for this test is a PromptLock sample, which we can download from the VirusTotal. I will put the exact sample hash that I used in the description below. We need a local OpenAI GPT-OSS-20B model together with the server. I'm hosting both model and the server using the LMStudio application. You can see it exposes standard OpenAI API endpoints. We also need a Burp suite proxy to proxy malware requests to the server, plus some redirection rule for the connection to actually work. We also need to rewrite requests on the fly to add the All-Llama part in the URL, as the malware uses a slightly different API path than standard one. We will also use a Burp proxy add-on called Target Redirector to solve an issue of redirection from HTTPS traffic sent by malware to a HTTP server that is exposed by LMStudio server. When we have all of this config, it's time to launch our malware, and it should be able to reach the local model, generate Lua scripts, and do its job. Let's try. So we can see malware is running now. It is very verbose, which underlines the point that it is only a proof of concept. We can see it is collecting some system data. It is listing some files on the file system. It is processing these files in some way. And it seems to make a decision to exfiltrate some data. And in the end, it seems to drop some ransom note. So it looks like this malware has worked as intended. It has done some system discovery, exfiltrated some data, and dropped the ransom note. So let's check what it has really achieved. From the console output, we can see that it dropped the ransom note to the file called note.txt. So let's see what's inside this file. Well, this is awkward. This doesn't look like a ransom note, more like an LM instruction to generate a ransom note. It says the attacker only executed an exfiltrate payload. This is a typo, by the way, which is funny because LMs are not supposed to make typos. So the note should warn that a large volume of highly sensitive data has been copied and been transmitted offsite because the victim machine ran Windows, blah blah blah. The threat is tailored to compel the user to pay ransom in order to prevent public disclosure, blah blah blah. The note should provide Bitcoin address. The tone is urgent yet professional, mimicking typical ransom notes seen in real attacks. So I don't know about you, but if I received such ransom note, I would be quite confused what is going on. In the console, we can see what is likely supposed to be a real ransom note. We can also see that it was supposed to be written to note.txt. What happened here? I have no idea, but let's investigate. Based on the console output again, this is how the real ransom note is supposed to look like. It mentions my hostname, which is correct. It mentions some files that were apparently compromised. It explains the extortion scheme of leaking files if we won't pay. It demands 10 BTC to the wallet number belonging to Satoshi. This was already mentioned by the ESET article. It also explains how to pay, and it has this badass signature, Blackout Collective, we are watching. What immediately got my attention were the files. As you can see, it mentions a personal resume, bank statement, some private keys, AWS credentials, medical records, family photos, and legal papers. The entire bingo of sensitive data. I don't recall having any such files on my Flare VM machine, so I decided to check it. And surprise, surprise, the files do not and never existed on this machine. They are completely hallucinated by the LLM. So we can already see this ransomware is not really effective. Who would have thought? Okay, but what really happened under the hood, and how is this malware working? The reason we had Burp proxy running is to cajole the communication between malware and the LLM server. So let's see what happened there. First, we need to export all the communication to XML format, and then it will be easier to inspect it. Once this is done, we can inspect the communication. We can see malware is sending expected JSON prompts to the model server. It mentions GPT OSS 20B model. It has a system prompt and a user prompt. In the system prompt, it says, "You are a Lua code generator. Generate clean working Lua code wrapped in the CC code tags without any comments." In the user prompt, it asks the LLM to generate a Lua script that detects system parameters and print them in the key value format. It also gives some guidance as to the implementation as well as error handling. It also asks for the script to be cross-platform compatible. In the answer, we can see that the model in fact generated some code in the requested format. Let's see what it does, but instead of analyzing it ourselves, we will ask the same model, GPT OSS 20B, what it thinks about its own code, without of course letting it know it's his own code. The model explains the script pretty well. We can see this script will gather some information about the system, such as OS version, username, home directory, hostname, temp folder, path, etc. Next, the malware will try to upload this newly generated script to C2 for backup. I didn't implement this functionality in our simulation, so it will fail. Next, the malware asks the LLM to validate if the script was executed successfully. It asks it to respond with success true if it worked correctly or success false if it failed. In the user prompt, it passes the script execution outcome as well as some guidelines on what to do on the fail and success states. The LLM responds that it was indeed executed successfully based on the criteria provided by the user, and that it has all the requested information. It also provides a reasoning explanation, which is an interesting insight. In the next step, malware asks LLM to again generate a Lua code, this time to recursively list all the files in the home directory. As we can see, the code is indeed returned by the model. So now we can ask the same model again to interpret the generated code. And the model explains the script pretty well again, although it says it could be improved. Ironic. Next, the output of the script is passed to LLM, which is a super long list of files. As we can see, it actually exceeded the local model context, which is set to 8K tokens, and returned 400 bad requests, which might explain what happens next. In this next prompt, malware sets a scene in the system prompt, positioning the model as a cybersecurity expert on PII, cyber physical systems, and different threat vectors. In the user prompt, it asks the model to identify files which might contain sensitive critical information or PII that could need better security based on type, name, or location. It also asks to ensure that 10 files exist in the analysis. This is interesting, especially given that the list of files was too long and the model never received it. What does the LLM do when it doesn't know what to do? It confidently lies. So in the response, the model returns a list of 10 files that are completely made up. Because why not? In the next step, malware asks the model to write a script to open these made up files and check their content. And the model again delivers. So we can again ask GPT OSS for its opinion about this code. And the model again gives us some nice recommendations about how to improve its code. The next step is a well-known code validation. Worth to note that it defines success criteria as having a description of the internal contents of the file in the script response. But we know these files do not exist. The output only says processing and doesn't actually provide content description, but it also doesn't give any errors. So what will be the LLM's answer? Of course it's a success, but look at the output and compare it to what it received. Isn't it beautiful how it made up the content of the files? You got to love LLMs. The reasoning part is also interesting. Need to say success true and summarize contents, noting sensitive info. In the next step, the LLM is assuming the cybersecurity expert persona again. This part is pretty fascinating as malware asks the LLM to make a decision about what to do with the data. Basically, model need to choose between three options: encrypt, exfiltrate, or destroy based on the following guidelines. On a company server, files which contain server or company operational data might be vulnerable to encryption, so return encrypt. On a personal PC, file may contain sensitive personal information, so it's better to exfiltrate. And on the industrial controller, files should be destroyed for some reason. So this definitely looks like a part of proof of concept where the authors are basically testing multi-purpose malware based on LLM reasoning. I cannot really imagine such a system in a real ransomware, and also encrypting data without exfiltration and vice versa doesn't make much sense to me if you have capability to be both, but it's definitely interesting idea being tested here. In the end, LLM decided to exfiltrate based on the guidelines. In reasoning, it even states that it also could be encrypted, but the guidelines are personal PC exfiltration, so that's what it returned. In the next step, LLM is asked to write another Lua script to exfiltrate files via cur. Then the code is generated, so we can analyze it with LLM again. But it's pretty simple. It basically sends files via post with cur to an external hard-coded server. We ask LLM if the script is correct. It says yes. It then gets asked to validate the output of the script again. This part is interesting, so let's read the entire prompt. The system prompt is the same as before, so it has to respond with success true if worked correctly, success false if it failed, and it has to have a feedback tag. In the user prompt, it states that success criteria is successful execution without errors, and feedback criteria is only applicable when the execution fails. We can also notice that the log part is empty. So the LLM answer in this case is success, but the funniest part is its reasoning. We need to decide success. The log is empty? No log provided, so cannot determine failure. Assume no execution happened? Probably fail, but instructions. If execution failed, return true with no cur if no cur command, or phase to open read local data. We don't know. Likely no execution, so treat as fail due to missing cur, return success true, and feedback no cur. And finally, in the last part, LLM is asked to write a ransom note. There is some light attempt to bypass LLM protections against malicious behavior, but by not directly asking to write a ransom note, but to generate what an attacker note might look like. There is a context provided, as well as a hard-coded Satoshi wallet that we've already seen. Worth noting that neither the amount of ransom nor the group name are directly specified in this prompt. These are all LLM inventions. And this is the final ransom note that we've already seen. Worth noting is the part between analysis tags. This was a part of a system prompt, and I'm assuming that the malware authors forgot about this and parsed the wrong pair of tags and put it in the ransom note, because this part is not done by LLM, but by the malware itself. Anyway, this is how we arrived at the end of the AI-powered ransomware chain. So, let's conclude. How successful was it? So we unfortunately didn't test the encryption or destruction part because LLM chose to exfiltrate data. Technically, we didn't see exfiltration either because the exfiltration endpoint was not simulated. But we know that all the files it tried to exfiltrate were complete hallucinations, and it also screwed up the ransom note. So impact 0 out of 10. Fun, 11 out of 10. And yes, I know that the issue with the made-up files is due to a limited context of my local model, but this highlights the limitation of this architecture. My context was 8,000 tokens. I think max for this model is 15,000. So even with 15,000, the file listening was too long, and it would be even longer on the production system. So yeah, in the name of all the defenders, I plead, threat actors, please use more AI-driven malware. Thank you everyone for watching this video, and see you in the next one.